All right, so we're going to pick up looking at these formulas for vectors. Now, these formulas are all formulas that can be done without drawing. Okay, so that was the focus yesterday, kind of looking at how you can sketch it. Today, we're going to do less sketching. Okay, in the formulas that I'm going to put on the board, I'm going to call the two vectors that I use v and w. And remember, those are bold because they're vectors. And alpha just represents a scalar. So remember, when you scale a vector, there's three things that can happen. Can someone remind me, what are the three things? Yep.
It can get bigger, smaller, or flip.
Yep. It can get bigger, it can get smaller, or it can flip direction. Yep. All right, so the first thing we're going to look at is how we can add two vectors together, but we're not going to draw it. All right, so first of all, to add two vectors together, they have to give you two vectors. Okay. In the x and the y spots, those would all be numbers. Like that. Right? They'd all be numbers. Okay. The old way of adding two vectors together was take your first vector, take your second vector, line it up so that the end of the first vector and the beginning of the second one look just like that, and then connect where you started to where you stopped. Well, now, if we want to add two vectors together without drawing it, all we have to do is take the horizontal component of the first vector, take the horizontal component of the second vector, and add them together. And that's the horizontal component of the sum when you add them, combine them together, okay, without drawing it. Right? And same thing for the y's. If you want to get the vertical component, when you add two vectors together, take the vertical component of the first vector you're adding, take the vertical component of the second one, and add the two together, and that's the new vertical component. Same idea with subtraction. Okay, with subtraction, when we did it visually, there was one extra step. We had to take the second vector, flip it around, put it on the end, and then draw in our diagonal. Well, this time, all we have to do is subtract the components. When you do subtraction, the order matters. Okay, so make sure you do it in the order that they ask you to. So if it's v minus w, take the component from v and subtract the component from w. x1 minus x2, that's the horizontal. y1 minus y2, and that's your vertical. And what do we call that? That represents a number. Okay? But when you put a number in front of a vector, does anyone remember what you call that number? Yeah, you could look at your notes too if you have it written there, maybe. Yeah?
Scalar.
A scalar. Okay, so that's a scalar. Says it right there. So that's a scalar. Remember, when you scale something, the idea of this is you would take a vector and you would put multiple copies together. Like if you were trying to find 5v, you'd take v, you'd copy it 5 times, and you'd stack them all together. Well, depending on how big you're scaling it, you could have to draw a lot of vectors. So that drawing it isn't always the most efficient way to do it. So if we want to scale a vector, think of scaling as it's like a distributive property. You multiply each component of your vector, the horizontal and the vertical, by the number you're scaling by. So you just distribute it to each component. Right, and the last part, we have a vector and we have the double bars around it. What does that symbol mean when you put double bars around it? Yeah. So absolute value is usually when you put single bars. What does it mean when we put the double bars? It's a little bit different. Yeah?
It's the magnitude.
It's the magnitude. And what does magnitude mean?
It's like how long it is.
Yeah, it's how long it is. So if we go back, we had this one already drawn yesterday. Let me do it again real quick. 3, 1, 2, 3, 4. That's the vector 3, 4. It goes 3 to the right, and it goes 4 up. So I think I had drawn this in one color. That was 3 units. And that was 4 units. Okay, what I want to look at now is how we can find the length of the vector in black. Right? That's the magnitude of the vector. Yeah, we can get the length of that vector in black. Yeah?
Pythagorean theorem.
Yeah, we just use the Pythagorean theorem. So to find the length or the magnitude of a vector, you use the Pythagorean theorem. Take the horizontal component, square it. Take the vertical component, square it. Add them together, and then take the square root. That's the formula for the magnitude. There's each component squared, added together, and then take the square root. So it's just Pythagorean theorem. All right, so let's try, we'll try each of those formulas. Again, we're not going to do any sketching, but we're going to add, subtract, scale, and find the length of these vectors. All right, so let's start with adding them up. Since they gave us the vector in unit vector notation and the algebraic notation, we'll do our answers both ways. Okay, let's start with unit vectors. What's going to be my horizontal component when I take v and w and add them together? Yeah. 5. If we're writing it as a unit vector, what would we need to put with that?
Oh, 5i.
5i. So 5i. And what's going to be the vertical component when I add v and w together?
Negative 1.
-1j. So you could put -1j, or you can just put -j. And so that's the answer in unit vector form. Or how would I write the answer using the angle brackets?
5 and -1.
So you said 5, and what would go after it?
-1.
-1. Yep. So that's just two different ways of writing the same thing. Okay, 5, -1. Okay. Any question how we added those together without any sketch? All right. So now let's subtract the two vectors. Okay, so again, no drawing. We're not going to take the second vector and flip it around and put it on the end. We're not going to do any of that. What's going to be my horizontal component when I take vector v and then subtract vector w? Yeah?
-i.
-i.
Plus 7j.
And the vertical component is going to be a plus 7j, because it's 3j minus 4j. So that becomes plus. So -i plus 7j. Or if we want to write it in the other notation, how would I do that? Yep.
-1, 7.
-1, 7. So in this notation, you don't need to put the -1 in front of the I. You can, but you don't have to. In this notation, you have to. If you don't put the -1 there, you would be blank. So you got to put something. Okay. All right. Any question on v minus w? Okay, so the next one is a scalar product. If we were doing this on paper, you'd take v, you'd make 3 copies and stack them all together. But when we're not going to draw it, we're going to think of it as just distributing the scalar to each component of vector v. So for this one, you do not need w. Okay. The last two, you needed v and w. This is just v. So anybody think they could tell me what 3v would come out to? Yep.
6I, 9J,
6i, and then what comes after it?
9J,
And what comes between the I and the 9?
the comma.
No, not a comma in
Oh,
this
sorry,
notation.
plus.
You have to put a plus, yeah. So if you put 6i comma 9j, technically that'd be wrong because it's not really either format. It's like a mixture of the two. So 6i plus 9j, or 6 comma 9 with the angle brackets. Okay, so when you're using the angle brackets, don't use i's and j's. And when you're using the i's and j's, don't use the comma or the angle bracket. Okay. What did we say yesterday? When you add two vectors together, the result is what in general?
New vector.
A new vector. How about when you subtract two vectors? You get a new vector. And when you scale a vector, you get a new vector. Well, the last operation is not a vector. When you find the magnitude of a vector, the answer is not a new vector. It's just a number, like 7 units long. So we're going to find our magnitude. Just copy down the formula. x1 squared plus y1 squared. Now we just have to fill it in. Okay. This time, again, you're just using vector v. You do not need w to do this one. What's going to be the first number that we square? 2, yep. And the second number?
3.
3. Okay. So let's find the magnitude. 2 squared is how much? 4. And 3 squared? 9. 4 plus 9 gives me 13. So if they want an exact answer, that's how you leave it. What else? If you can reduce the square root, you should. So if you get something like, I just made that up. We didn't get 20 in this problem. But if you did, remember you should reduce that to square root 4 times square root 5, which is 2 root 5. So anything we already know about square roots, that still applies here. Okay. All right. Any question on add, subtract, scale, or magnitude? And that's all without any sketching. Okay. All right. Can someone remind me again, if you have a magnitude that's equal to 1, that vector has a special name. Does anybody remember the name of it?
Unit vector.
It's called a unit vector. Yeah. So what I want to look at now is if we have a vector that's not a unit vector, how can we make it a unit vector? In other words, if you've got a vector that's not 1 unit long, let's say like the black one, let's say it's too long, how can you shorten it so it's exactly 1 unit? So let's say we had, let's make a table. Let's say put the magnitude in one column, and then I'm going to put what we would have to scale it by to turn it into a unit vector. What if we had a vector that was 5 units long? What would you scale it by to make it 1 unit long? 1/5. Okay, so we're looking for like a pattern here. What if you had a vector that was 8 units long? What would you scale it by to turn it into a unit vector? You'd scale it by 1/8. What if you had a vector that was 1/3 of a unit? What would you scale it by to make it a unit vector?
3.
You'd make it 3 times as long. So if you know the magnitude, what's the connection with what you scale it by? Yeah?
You just flip it. So
You flip it.
reciprocal.
Yeah, it's the reciprocal. So if you had a vector that was a magnitude of x, what would you scale it by to make it 1 unit long? What is it?
1x.
Well, scaling it by 1 would keep it the same.
1 over.
1 over x. Yeah, the reciprocal. All right. So what we're basically trying to do here is we're finding a unit vector, and I'm going to give you some vector. If the vector that I give you already is a unit vector, well, then there's nothing to do. But if I don't give you a unit vector, you are finding another vector, and it's going to point exactly the same way as the original one. You're just going to make it 1 unit long. So if it's too short, you're going to make it a little longer. If it's too long, you're going to shorten it. So you're going to make it 1 unit. And we saw the pattern to do that is if you have, let's say, the vector v, you multiply it by the reciprocal of its magnitude. Right? So you take the magnitude and you flip it. So basically you would do this. That's what you would scale it by. Take your vector and take the reciprocal of the magnitude, flip it, and multiply the vector by that. And that'll force it to be 1 unit long. But you do have to flip the magnitude. If you don't flip it, it won't work. And if you want to simplify it, you can put that together like that. That's the same thing. And I wrote that down right there. So taking a vector and multiplying it by 1 over its magnitude, or dividing it by its magnitude, same thing, will result in a unit vector. Okay, so the first thing you need to figure out when you're doing this is that. If your vector is already 1 unit long, you're done. There's nothing to do. If it's not, well, then you use the formula. Okay, so let's try this one. So it says to find the unit vector that corresponds to 3i minus 4j. All right, so what's the first thing that I should figure out about my vector? Yeah, find the magnitude, right? If it's 1, then there's nothing to do. If it's not, then we got to fix it. So again, write down your formula. And what's going to be the first number that I square? 3. And the second number?
4.
You could use 4 or negative 4. It doesn't really matter because when you square it, the negative is going to cancel out. What's 3 squared give me?
9.
It's 9. And negative 4 squared?
16.
And what about when we add 9 and 16 together?
25.
25. So what's the magnitude of my vector?
5.
5. Okay. Now we can answer the question, is it a unit vector? No. For it to be a unit vector, it would have to be how long?
1.
1. That's 5. That's not a unit vector. It's 5 times too big. So what are we going to scale our vector by? 1/5. That's what we need to find. So it's 1 over the magnitude. So it's 1/5 times 3i minus 4j. If I do that out, what's 1/5 times 3? 3/5. So that is your new horizontal. And what's 1/5 times negative 4? Negative 4/5. So that is a new vector. It points exactly the same way as the original vector, but it's 5 times shorter, and that makes it a unit vector. You don't always scale by 1/5. It depends on your vector. Okay. So you gotta always scale it by the reciprocal of its magnitude. But in this case, it was a 5. All right. So any question on how to take a vector and turn it into a vector that's always one unit long? And as far as should you use decimals here, I would probably just stick with fractions. Okay. All right, so the last thing we'll look at in 5.4 is an application of a vector called a velocity vector. Okay. When you describe velocity, vector is perfect. What are the two things that you have to know about an object's velocity to describe how it's moving? There's two things you have to know. Yeah?
Is this one speed and distance?
You need to know the speed of it. So that's definitely important. How fast is it going? How fast it's going. And there's one other thing you need to know, but not distance.
Direction.
Direction. So when we're writing a velocity vector, we are describing how fast something is going and the direction that it's going in. Okay. So let's see if we can come up with a formula to do that. Now, when we write vectors, how many components do they have? At least the ones we've done so far. Two. They have a horizontal component and a vertical component. So when we write a velocity vector, we need to figure out a horizontal component and a vertical component. So let's say that this represents our vector. Now, normally if you were to throw an object, it wouldn't keep going in a straight line because of gravity, it would curve back down. But we'll pretend that we're in an environment without any gravity or air resistance. So once we throw an object, it just keeps going straight forever. Now we have to figure out a horizontal component and a vertical component. And we can do that by turning that into a certain shape. Anyone have an idea of what shape we're going to make out of this? And we kind of already did this shape earlier, back when we talked about magnitude. We're actually going to do kind of the same thing. Yeah?
Triangle?
Yeah, we're going to make a triangle out of it. So the way I'll make a triangle is I need just a vertical. That works. And the horizontal component of this vector is what's in red. The vertical component is what's in blue. And this is a right angle. Okay. So I need to find the length of the red side and the blue side. And what they're going to give you in the problem is they will tell you the angle that the object is being thrown at. So just to explain what that means, a 0-degree angle would mean it's perfectly straight, kind of like a pitcher would throw it in baseball, just pretty much straight. 90 degrees would be straight up. Okay. It's usually some angle between 0 and 90. That's how we're throwing it. If the angle went past 90, well, then that means you're throwing it behind you. But it's going to be between 0 and 90. And then they'll also tell you the speed. Okay, so those are the two things that they're going to tell us. Okay, we don't know what this angle is, so we can just call it theta. But when you have an actual problem, you'll know what it is. And that vector in black I've called v. I could have made it a bold v. I did the v with the arrow this time. All right. And let's label our two components. Let's call the horizontal component x and the vertical component y. These two things are going to be given to you. What trig function could I use? Let's start with x. That would relate this side and this side to that angle. Yeah.
Cosine.
Yeah, it's cosine. I was thinking something else. Yep, cosine. So cosine of your angle equals, what's our definition of cosine?
Adjacent.
Adjacent over hypotenuse. Now, when we say adjacent over hypotenuse, what do we mean, like, adjacent? What about the adjacent? Like, the color of the adjacent side, the weight of the adjacent side? Like, what about the adjacent? The length, yes. So we need the length of the adjacent, which is x, over the length of this vector. So we don't want the vector, we want the length of the vector. What do we call the length of a vector?
Magnitude?
Magnitude, yep. So you don't want the vector in the bottom. You want the length of the vector. If you put the vector in the bottom, that would literally be like putting x over an image. That doesn't even make sense. You're not drawing a picture in the bottom of your fraction. You're putting a number. All right, so now, if we get x by itself, how would you move this magnitude of v to the other side? Yeah, multiply. So if you multiply it, you've got magnitude v, cosine theta, and that is the formula for the horizontal component of a velocity vector. Now we got to do the same thing for the vertical. What trig function could I use that would relate this side, this angle, and that side? What is it?
Sine?
Yep, we can use sine. So the sine of the angle that the object is thrown at equals, and what's our definition for sine?
Opposite over hypotenuse?
Opposite over hypotenuse. Okay, the opposite side is y. And when we say hypotenuse, we mean the length of the hypotenuse. So we need the length of v, and again, that's the magnitude. All right, so what would be the formula for the vertical component of the vector in black? Yeah.
The magnitude.
Magnitude of what?
Vector.
Of the vector v
Sine angle.
times the sine of my angle. So that is the vertical component. Now let's put it as a vector. Remember, when you write a vector, it's always the horizontal component with an I plus the vertical component with a J. So let's substitute in our formula. Horizontal component is magnitude v cosine theta. And then put an I next to it. So we know that's the horizontal. And then magnitude v sine theta, and put a j next to it, so we know that's the vertical. So that's the formula for a velocity vector. Theta is the angle that the object is thrown at, which is given to you in the problem. And the magnitude of the vector is the speed. Right? Magnitude means speed. It's the same for the other two. Angle you throw the object at, and the speed. All right, so now, using that formula, I already wrote all that down, so I'm just going to get rid of that page, and I'll just keep this page. So we're throwing an angle at 50 miles per hour at a 30-degree angle. So the first thing to understand is not all the energy is moving the object forward. Okay? Some of the energy is moving the object up. So we want to find a formula for the velocity vector, and they want us to write it with i's and j's. That's what unit vector form means. That's exactly how I gave you the formula right there, with i's and j's. Okay, so first, let's just identify those two things. What's theta in this problem? 30 degrees. That's the angle we're throwing the object at. And what's the magnitude of our velocity vector? Magnitude means speed, yep, when you're talking about velocity. So now we just have to plug in those two numbers in those spots and see what we get. Okay, so for our velocity vector, we've got 50 cosine 30. That's the horizontal. And the vertical is 50 sine 30. And remember, those i's and j's are supposed to look bold because they're vectors. All right, let's type that in. And looking at my calculator, what's the first thing I should do to start to type each of those in?
Put it in degrees.
Put it in degrees, because those angles are not radians, and right now I am in radians. That's the first step. Change it to degrees. Now, 50 cosine 30, we don't need to close the parenthesis because there's nothing else. So it's 43.30 I. Plus, and then 50 sine 30. 25J. That is a vector that describes an object being thrown at a 30-degree angle at 50 miles an hour. Okay, so what do we call this part? Part I just circled in blue. Yeah. The horizontal component. So what do you think that means in this problem? 43.3. Like if we were to actually do this in real life, 43.3 would be something. What would it be?
How far?
No, it's not a distance. This is all velocity. So there's no distances in there. Because remember, technically we're doing this without any gravity, no air resistance. This object goes for an infinite amount of time. It just goes forever. Yeah?
How fast you're traveling at that point?
How fast you're traveling? Well, we're traveling 50 miles an hour at a 30-degree angle. But the 43.3 is
That's how fast you're going to the side.
horizontally, yeah. So that's your horizontal speed. What that means is if you were standing in front of this object and it was coming straight at you, and you pointed like a radar gun at it, it would be coming at you at 43.3 miles an hour. It's not coming at you at 50. It's coming at you at 43.3. And the 25, what do you think that number is?
Vertical.
That's your vertical speed. So what does that mean? Well, that means if you were in like a helicopter above the situation and you pointed a radar gun down at the ball, the second the ball leaves the person's hand, it's going 25 miles an hour upward. This speed in real life would change, because what would happen is it would start going fast at first, but then gravity would slow it down and eventually it would reach its highest and then it would come back down. This number, if you don't include air resistance, would never change. So when a pitcher throws a baseball, the speed that it leaves their hand at and the speed that it hits the catcher's glove at is probably pretty much the same. The only reason it would change a little bit is if air slows it down. And there's really no vertical speed when you throw a ball as a pitcher. You don't really throw it upward. You just pretty much throw it straight. Maybe a little down, but pretty straight. Okay. Any questions on that? All right. All right, so our second to last lesson for this week, and actually really the only new thing we're going to learn left, is called dot product. And I say that we're not really learning anything new when we get to the next section, which is 5-6, because 5-6 is 3D. But all that 3D is taking everything we've already done in 2D and just doing it again in 3D. So the 5-6 is kind of like a review. Extending it to 3D is very, very easy. All right, so this will be our last new concept for the week. This is called dot product. So what have we done so far with vectors? We've taken two vectors and added them. We've taken two vectors and subtracted them. We've taken a vector and scaled it. And we found the magnitude. What we haven't done is something like this. Take a vector and multiply it by another vector. So first thing to understand is when you want to multiply a vector by a vector, there are two ways to do it. So if somebody said to you, multiply this vector times that vector, I'd have to then ask you, which way do you want me to do it? Do you want me to multiply them using what's called a dot product? So there's a set of rules I use to do it that way. Or do you want me to multiply them and do a cross product? There's a different set of rules to do it that way. Cross product, first of all, is something you can only do in 3D. So that's why we're not talking about it. If we were going to talk about it, it wouldn't be until tomorrow. But we don't get into what's called the cross product in this class. Okay, so we only talk about one way to do it, which is the dot product. So that's what I'm going to show you right now. So when we are doing a dot product, first of all, I need to give you two vectors. When we do an actual problem, it'll look something like that. I'll give you some numbers. Each vector has a horizontal component. They can be the same or they can be different, any two numbers for I, in front of I. And then each vector also has a vertical component. Again, those can be any two numbers in front of J, positives or negatives. But A1, A2, B1, and B2 would all be numbers. Just like that. To find the dot product between two vectors, it's very easy. All you have to do is take A1 and A2, multiply them together. Take B1 and B2, multiply those together. And then add the result. That's called the dot product. So multiply the two numbers, two horizontal numbers, multiply the two vertical numbers, and then add the result. When you write dot product, you do have to use that symbol. You put a small dot between the two vectors. And that's because if you were going to do cross product, we would write it this way. Okay, that's called a cross product. You put a little X between them. Okay, but we're just doing dot product. Now, since A1 and A2 are numbers, what do you get when you multiply a number times another number? Like in general. You get what? A new number. How about when you multiply another number times a number? Another new number. And if you take a number plus a number, what do you get? Another number. Okay, so the point is when you do a dot product, the answer is a number. 5, -8. Okay, it's just a number. That number means something. I'll show you what the number means in a little bit. But first, let's just see if we can find the dot product between those two vectors. So we've got V is 2i minus 3j, and W is 5i plus 3j. So first thing you want to do is write out your formula. You're going to multiply two things together, multiply two other things, and then add them up. That's the whole calculation. All right, so if I want to do v dot w, what are the first two numbers I would multiply together using that as my example? Yep.
2 and 5.
2 and 5. So v dot w, you want to do v first, w second. We'll see what happens if you don't do that in a minute. So 2, 5. And what are the next two numbers we multiply together?
Negative 3, 3.
-3 and 3. Okay. 2 times 5 gives me how much? 10. And what's -3 times 3? -9. What's 10 plus -9? So the dot product of these two vectors is 1. That's it. That's how you find the dot product. Any question on the calculation? Because now I want to try it as w dot v. Let's see if there's a difference or not. So w dot v means the number from w first, the number from v second, in that order. So what would I put in my two parentheses if I want w dot v? Yeah? 5 and 2. So 5 times 2. And what about in my second parentheses?
3, -3.
3, then -3. But what happens when I find the dot product doing it that way? It comes out the same. There's a name for that. I think we talked about it yesterday. What does that mean if you can switch the order and you still get the same answer? What property? Commutative, yeah. So it doesn't prove anything, but it turns out this works all the time. So the dot product is commutative. So v dot w, switch the order, w dot v, comes out exactly the same. Any question on that one? Okay, so let's try v dot v. Okay, v dot v just means you don't need w. You're just going to dot v with itself. Pretend that the two vectors are the same numbers. So if I want to do v dot v, what's the first thing I would write down in my parentheses?
2 and 3. Or -3, I mean. Just 2 and 2.
2 and 2. Right? Pretend that this is 2i minus 3j, and you have another one, 2i minus 3j. Same thing. So it'd be 2 and 2. 2, 2. And the second part?
-3, -3.
-3 and -3. Okay. And what would that give me a dot product of?
4. Wait,
Total final answer.
13.
13. 4 plus 9. Okay. Any question on finding the dot product there? So remember, dot product is just a number. Okay, let's try this one. Okay, it's written in a different notation this time. It's the first notation we learned, not I and j. We're going to take the vector 2, 6, and we're going to dot it with the vector 0, 0. What would be my first calculation that I do?
2 times 0.
2 times 0. Plus, and my second part?
6 times 0.
6 times 0. And that gives me a dot product of what?
0.
0 the number or 0 the vector?
0 the vector.
Well,
Another number there.
when we find a dot product, remember we went through, it's always a number plus a number, which is a new number. So the answer here is 0, the number. Don't make it a bold 0, don't put an arrow on top. Just 0, the number. When the dot product comes out to 0, that means something. Okay, so we'll look at what that means in a second. Any question on that? Okay, so that's how we find dot product. You can do distributive property with dot product. So like if you had 2 vectors in parentheses and you were adding them, and you wanted to find the dot product of that with the sum of those, you can distribute U, just like I did there, as a dot product to V and a second dot product to W. So distributive property works. Probably not something we're going to use that often, but it does work. All right. So what's the whole point of the dot product? Well, if you had a vector like that and another vector like that, sometimes what we want to try to figure out is that angle. What is the angle between the 2 vectors? Now the angle is always somewhere between 0 and 180. It never goes more than 180. Because when you draw vectors, you're always looking at the angle that's between the 2. You're never looking at the angle that's on the outside. Okay? So the maximum it could be is 180. All right. So how do we find that angle? Well, there's a formula. And the reason there's a cosine in the formula is because this comes from the law of cosines. So we studied that a few weeks back. And technically, you don't need this formula. You could use the law of cosines to figure it out. It will take a lot longer. This is much, much faster. So to find the angle between 2 vectors, you need to figure out 3 things. First one is the dot product. Second one is the length of your first vector. And the third one is the length of your second vector. Once you have those 3 pieces of information, you fill them in. And then you solve for theta. Now, right now, this formula is not solved for theta. It has a cosine on this side. How do we get rid of cosine? Yeah?
Inverse cosine.
Yeah. So you're going to have to use inverse cosine as the last step in this problem. Okay, this is the last thing we're looking at today. So we'll find some examples, and well, I have some examples. We'll find some angles, and then we'll see how many we get through. If we finish them all, great. If not, we'll finish them tomorrow. So just in case you're not clear what the denominator is, that's the length of U times the length of V, the magnitudes. All right. So here's our 2 vectors, and we want to find the angle between them. If we sketch them real quick, we can kind of estimate what the angle is just looking at them. So let me go like this, and let's put a background. Maybe this will work. Yeah, it's too small. That's good. All right, so we have one vector that's 4i minus 3j. So if I start here, 1, 2, 3, 4, 1, 2, 3. That's one vector. Doesn't matter where I put it. The second one matters. I want the second one to be at the same spot that the first one started at, so I can see the angle. Right 2, up 5. Right 2, 1, 2, 3, 4, 5. That's the angle that I'm looking for, right there. How big does it look like that angle is? Just kind of like an estimate. Yeah?
Around like 100.
Yeah, maybe around 100. It's definitely more than 90. I don't think it's more than like 110. But yeah, probably around 100. So let's find the angle and see if it comes out to around 100. Okay, so let's start with our dot product. First two things I'm going to multiply together are what and what?
4 and 2.
4 and 2. Yep. Okay, second two things we're going to multiply.
Negative 3 and 5.
Negative 3 and 5. That gives me 8 minus 15. What's going to be my dot product?
-7.
Yep, -7. Okay, so that's the first thing that I need to find the angle. I need the dot product. Magnitude of u. So magnitude, that's what we covered that formula earlier today. So square root, and then you fill in each component. When you're finding magnitude, what formula is this really?
Pythagorean theorem.
Yeah, it's just a Pythagorean theorem. It's the base and the height. All right. So for u, what are the two numbers I would fill in?
4 and -3.
4 and -3. And that's going to come out to a nice number. What's going to be the magnitude of that vector? 5, yeah. It's just like going like this. Right, you just make it a triangle. 1, 2, 3, 1, 2, 3, 4. That side's 3, that side's 4, that side's 5. Okay. And how about the magnitude of v? What are the two numbers we're going to fill in?
2 and 5.
So 2 squared plus 5 squared. It doesn't come out nice, so we'll just leave it as a square root. And what does that give me?
Square root of 29.
Square root of 29. Again, if you get stuck or you don't remember how to do it, just make a triangle out of it. 2, 5, and then do Pythagorean theorem. Square root of 29. All right, so now let's plug that all into our formula. What was on the left side of the formula?
Cosine.
Yeah, the left side. Cosine of theta equals, what was in the top?
E times
U,
The dot product.
the dot product. U dot v, which was -7. And what was in the bottom?
Magnitude of u
Magnitude of u times
times
the magnitude of v. Yep. All right. So now we already mentioned this, but we got to get theta by itself. What do you do on each side to get rid of cosine?
times it by 5 square root of 29.
Yep.
Inverse cosine.
Right, we got to take the inverse cosine on both sides. And that is what the angle is going to be, and we thought it was around 100. So now let's see what it comes out to. So inverse cosine of -7 divided by 5 square root 29. If I type it in like that, it will come out wrong. What the calculator will do is -7 divided by 5 times the square root of 29, but I want it to do the denominator first. 5 square root. I needed an extra set of parentheses, but I want the 29 inside, not outside. Now it'll be okay. All right, so yeah, be careful if you need to type in something that has a product in the denominator, which most of the time you do. Put it in parentheses, and we get an angle of 105.07. Yeah, that's about what we thought, around 100. generally, 2 decimal places is good enough. Any question on finding the angle between those two? Now that's just a random angle. There's nothing special about 105.07. But there are a couple angles, if they come up, they are special. Anybody have an idea of an angle that if it came up, might be something special? Yep. 90, yep, that's a special one, because the vectors would be what we call perpendicular, or when they talk about vectors, they use the word orthogonal, means the same thing. So yep, 90 is an important one. There's another one.
180.
Yeah, 180. If you have 180, that would be like you had a vector like this, and another vector like that. Okay. Do those vectors cross each other? I mean, they start at the same point right there, but do they cross anywhere? No. And when things don't cross, what do we call that? Parallel. Yeah. So if you want to visualize it, a little better, you could put it down there and then see they are parallel. So 180 is parallel. There's also another angle that's parallel. Imagine drawing another vector just below this, but not pointing this way. Looks kind of like that, but just a little different. Yeah? Yeah, 0 degree angle. 0 degree angle would be like this. If you were to line them up, there's no angle between them. They both point in exactly the same direction. So when you're talking about vectors, 2 things that point exactly the same direction are called parallel, or if they point in opposite directions, that is parallel as well. Now, let's look at the case that somebody mentioned first, the one that looks like this. What's the angle right here if the 2 vectors are perpendicular? Yeah, this would be a 90. So let's work backwards from that and see what happens. Let's assume that we already know what the angle is between 2 vectors, but we don't know the dot product and we don't know their magnitudes. So it's like we're going to start on the left-hand side. Okay, you'd have the dot product in the top. I don't know what it is. And you'd have the product of the magnitudes in the bottom. Let's take the cosine of 90 and simplify that side and see what happens. Cosine of 90, 0. So if the 2 vectors had an angle of 90 degrees, this left-hand side would turn into a 0, because when you take the cosine of 90, you get 0. So what you would have is a fraction equal to 0. There's only one way that a fraction can ever equal 0. What's the only way that that could ever happen? Yep.
This is 0 on the numerator.
Right. The numerator has to be 0. What is in the numerator in this formula? The dot product. Exactly. So if you find the dot product between 2 vectors and it comes out to 0, you automatically know they are perpendicular. Because if this comes out to 0, it makes the entire fraction come out to 0. And if that fraction is equal to 0, that means you must have had a 90 plugged in for cosine, because that's the only thing you can take the cosine of and get 0, at least for the angle we're dealing with. So if the dot product is 0, the 2 vectors are orthogonal. Okay. So let's see if these 2 vectors are orthogonal. So find their dot product. If it comes out to 0, they're perpendicular. If it doesn't come out to 0, well, then all we know is they're not perpendicular. What would be the first 2 numbers we'd multiply together? 2 and 1. So if you want to pretend like there's a 1 there, that helps. You can do that. So 2 times 1. And the second part? 1 and 2. And what's going to be my dot product there? 4. That's a dot product of 4. 2 plus 2. So now we should be able to answer the question. Are these vectors orthogonal or perpendicular? It means the same thing. Are they orthogonal? No, they're not. What is the angle? I don't know. We'd have to go through and do the whole problem. If you can change one thing here, what could you change to make them perpendicular? You can only change one thing. Anyone see what you could change? Yeah.
Make one of the numbers negative.
Make any one of the numbers a negative. Yep. Okay. If you make anything a negative here, you would get a dot product of 0. Yep. And then they would be perpendicular. That's it. Okay. Any question on that? Okay. And the last thing, I think we already said this, but if two vectors are parallel, then that means the angle comes out to 0 or 180. Unfortunately, there is no shortcut for parallel. Okay. If you want to know if they're parallel, you pretty much have to go through and do the whole problem like we did the first one. And if you get an angle of 0, it's parallel. If you get 180, perpendicular. 0 or 180 are both parallel. All right. So any questions on that? Okay, so I think I have like 8 or 9 questions from this section. So we'll do a few of them tonight, and then we'll do the rest of them with the homework from tomorrow. Okay. So let's do. Okay, so let's do 7, 9, and 11 from this page. So 3 questions from that page, and then I need the other page. I didn't write it down.
It's like 344.
Okay. So on page 352, each question has 3 parts. I think the first part says find the dot product. The second part says find the angle. And then the third part says, is the angle parallel, perpendicular, or neither? So it's all connected. Okay, so 3 questions on 352, and then most of the homework is on the first part of what we did. Okay, so we'll go over that tomorrow, and then we will finish up section 5, 6 tomorrow.